Hello and welcome to the very last video tutorial on Maze Solver. In this video, let me quickly give you an overview of what we have learned till now. So basically, we started with understanding a maze, and then we have gone through uh, the possible paths that appear whenever we are about to design and solve a maze. So these are the 8 possible paths that we have seen earlier. We got these end T, U-turn, cross, left, right, and simple right T and left T conditions. So whenever you're about to build a maze solver robot, you are about to encounter with these 8 possible paths. And then we have also seen how a robot traverses this particular path, and we'll be sticking with the same pattern till the end so that whatever path it records whenever our robot reaches the end, we will have the exact same uh, paths which are recorded here. So the path that even our robot, after building it practically, what it is going to record is going to be the same one. So this path has to be optimized, something like this. And finally, during the first iteration, it should be recording this path, and then it should be optimizing the recorded path to a final uh, RL path. That is, it should first of all travel right. If it starts here, it should first travel right and then it should travel left. So that's how the robot is going to reach the destination without crossing any of these unwanted paths. So we have also gone through some of the basic programming aspects of how to use the Adafruit library and attaining some of the basic movements like moving forward, backward, left and right whenever it encounters with a junction. And whenever we are about to scan a path, it is very important to have some sort of sensor. And I have also introduced you with a line sensor which has a specific geometric shape. And as a conclusion for that particular section of the tutorial, we have seen that whenever you have a specific uh, uh, kind of a line sensor which is arranged in a specific geometric pattern, it becomes a little bit easy for us to identify the junctions whenever we are coding. Alternatively, we can go for some discrete sensors where you are able to place the individual sensors as and where you need on the robot. So the placement is going to be a little bit flexible. I'm going to show you this in a couple of minutes from now. And then what we have seen is we have programmed the robot for following the line and then identifying the junctions. So basically these junctions are what we have programmed it for. And then programming robot to record maze path is our major task, which we have seen earlier. And then this is an optional part where we need to optimize the recorded path into RL. And then you may connect some sort of buzzer or some LED just to provide some audio visual indication that your robot has traveled through the complete maze path and it has optimized and now it is ready to travel uh, to the destination uh, by following the optimized path. So this is going to be the final video where we'll be programming our robot to solve the maze finally. So let's get started. So this is what we have here. This is the exact program what we have been referring and we have been programming in all of the previous videos. Now, a couple of things we need to understand. That is, whenever we're about to begin a new program, it's always a good task to start everything from scratch. So I have already opened up a new sketch and then I have named it with a name called Maze Solver Robot. So this is going to be our final program. I have kept it in a dual inline manner so that I can copy some of the part of the code which I have already explained you so that I can readily copy paste the code here. So what I'll do now is first of all delete the code in the new sketch. Now we need to do a couple of things here. So let me lay down or list down things for you, like what exact things we're about to do. So basically this is going to be a code which we are writing for maze solver. And then step number 1 is going to be record the path. Sorry for the spell mistake. Okay, so first thing is to record the path, and for recording we need to, okay, so this may not be in the chronological order, so let me put them in chronology so that it will be easy for you people to understand. Now the first thing is connect the sensor and scan for the junctions. Okay, after that we need to record the path and make the robot move in the respective conditions, whichever is applicable. And then check if destination is reached by the robot. And then number 4, optimize the recorded path. And then last but not least, which is going to be an optional step in our case, that is indicate the user uh, for readiness of the robot to follow optimized path. So this is what we'll be doing. We'll be first of all writing these codes, and then we'll be generating a couple of functions. So I'll readily copy paste the code what we have already done earlier, but I may change the numberings and some of the instances and the motors and the IC pinouts what I have used in our previous video. So I'll also intimate you what exact things we need to change as and when we are writing the code here. I'll make the things more clear to you people. Now, the first and foremost thing that we need to do is, of course, we need to include this header file, and then we also need these two things. So this is the header file, which is designed by the Adafruit um, um, vendor, and we are using the same motor shield like what we have seen in our first video. And now instead of calling it M3, I'll simply call it motor 1 and 2. So, and also I'll be making a small change here. So what I'll do is I'll be using pin number 1 from IC1 and pin number 4 from IC number 2 of the L293H bridge. So I'm doing this for a reason. So I for some reason don't have the motors rolling in a perfect direction whenever I'm connecting it on my side. So what I'm preferring is I'm simply trying to split down the two ICs so that whenever I'm driving my motor with either 12 volt power supply or 9 volt power supply, even though if it is having some rigid movement, even then the ICs won't heat up. So the reason number 1 why I'm using separate ICs for both the motors is that for having better current stability and for better heat dissipation, so that the complete current that a single IC is actually consuming is just for a single motor, so that ICs won't heat up. That's reason number 1. And reason number 2 is for some reason I'm not having a proper rotation on the same IC. So the simple way is, as we are having another L293D motor driver IC in spare on the same shield, it's always a good idea to switch that one. So you can either use instance or the pins 1 and 2 which count, I mean, which are M1 and M2 on our motor shield, or you can go for 3 and 4 here, which are M3 and M4 connections on your motor shield. Next, we also need to define a string variable to record the path. So I'm commenting these things. It's always a good habit to write some sort of comments down here whenever you're coding, so that it becomes easy for you people to read it as and when you're scrolling down through the code like this. Now next is we need to define the setup. There is not going to be a major change in this, so I'll quickly make these changes here. I'm not sure whether I'll be using this as motor 1 and 2, so I'll change it in a couple of minutes from now. Let me confirm it first of all, like what I have decided to use. Um, so one thing I would suggest here is whenever you're writing your final code, just go back through all the snippets of codes that you already written and then take down a page and note it down. So it's like writing or building some sort of pseudo code before getting into the real fight. Now, what we have here is I have the void setup, opening and closing brackets. Always do check for these things, otherwise you're going to end up with some abundant number of errors at the end, and then it becomes difficult to trace down all those things. Now, okay, so I don't need this line. Let me delete this. So we're writing this code so that we can print the scanned values that are coming out from our sensor and then weave it on the serial monitor. So we need this statement so that we could print something to the serial monitor. Next is we need this for loop, and we are writing this so that we are able to use digital pin numbers 14 through 20 on our Arduino board as an input where we are connecting our IR line sensor. So here I need, let me quickly change this. Okay, so we have completely finished the part till this one. Now it's better to save it, Control S, and then simply press Control R. And this is an important note that whenever you are writing very lengthy code, always write a part of it and then try to compile it. So I'm getting an error stating that error compiling for board Arduino Uno. What is the reason for this? Okay, maybe just because we don't have anything called a loop. This Arduino IDE by default expects two functions, that is void loop and a void setup. So let me add this empty loop function and then try to compile. Okay, so yeah, so I had this extra bracket because of which I'm having that error. Okay, now the sketch is compiled. I mean, we are ready to enter into the loop and then find the conditions for us. Now, before entering the loop, go back to what we have written. This is going to be a sort of pseudocode for our program. Now, I have connected the sensors and now we are about to scan for the junctions, means I'm about to write those if conditions which you have already written here. So I will copy the conditions one by one and then show you by pausing the video for a while, and then I'll directly show you all the conditions. So I'll just do it once for you with certain condition. Before that, I will add one more thing. Under loop, the major thing that we need to focus is the sensor position. So the sensor position which I'm using is like this. let me first of all put down the things. That is, I have sensor number 16 somewhere lying here, and then I have sensor number 14, sensor 15, and I guess 18 is here, and sensor number 19 is here, and this is 17. Okay, we don't need this. Fine. So what I have done here is, as you're already aware that we have used a line sensor array where I have 6 IR sensors which are placed on a common PCB, and we're calling it an IR sensor module. So you need to identify that we have defined 6 pins, 14 through 20, which are in total 6, and I have the IR sensor which is connected on the leftmost part of my sensor, connected to the the digital pin number 14. Similarly, the next leftmost sensor is connected to pin number 15, and I have the vertical upper IR sensor connected to pin number 16, and so on. So this positioning is going to be very much crucial whenever you define these conditions. So let me write one condition and show you. So it's better to have this comment as well, and then copy paste this one first of all. So now from this point onwards, from line number 30 and 31 onwards, we are going to scan for the junctions. So I'm currently writing the program for scanning the junctions. Okay, so I'm first of all scanning for the forward condition. So for forward condition, what we need is, if I have a black line somewhere here, okay, so that sensors 16 and 17 are falling on the black line, whereas sensors 14 and 15 are falling on the white surface, 18 and 19 are falling on the white surface again. So with this pattern in mind, with the X and the Y pattern in mind, I'm sure that my negative X-axis has sensors 14 and 15, positive X-axis has sensors 18 and 19, I mean the sensor numbers 18 and 19, whereas my positive y-axis has sensor 16 and negative y-axis has sensor 17. So keeping this pattern in mind, whenever I want my robot to move forward, I can write a couple of conditions. So the first condition is going to be something like this, what we have already written here. That is, if, let me take some another pattern. Okay, so let me copy this and paste. This is not yet a condition for front, but let me define the things for you. Now, currently what I'm doing is I'm writing a condition for forward direction. And here what I need is I want my sensor number 16, IR sensor 16 and 17 to be placed on a black line. And I'm sure that whenever my sensor is on a black surface, it is giving me a 1 output. So that I need to scan for sensor number 14 and 15 giving me a logic 1. So sorry, whenever my sensor is on black surface, it is giving me a 1. So my sensor number 14 is on white. That's why it is negative or so-called off. 15 is on white surface, it is off. 16 and 17 are on black surface, means it will be giving me a 1, means it must be on. So 16 and 17 must be on. Then sensor number 18 and 19 must be off. So I have put a negative sign here. Okay. So currently the condition of not digital read 14, not digital read 15, digital read 16, 17 true, and not of digital read 18 and not of digital read 19 is exactly giving me a condition which is going to be satisfied only when this 14, 15 are on white surface, 18, 19 are on white surface, 16 and 17 are on black surface. It's meaning that my robot is ready to follow the forward direction. So I have written a simple serial statement where I will be able to identify that uh, by watching the serial monitor that my robot is moving in the forward direction. But as of now, I am confident enough that uh, this is a condition whenever forward condition is attained, or junction where uh, there is a single line and my robot needs to follow the forward condition. So I haven't copied the front function and all yet, so I hope you can understand that. I'll at the end of this video, I'll copy down all the conditions for forward, backward, left, and right, and then show you if any extra functions to be defined. Now, here, whenever our robot follows the forward direction, our string variable, which we have already defined, has to be updated with an S. Here we need to take care, as I have stated earlier in the previous video, that this should not be repeated for recursive call of a friend function. A single call to a friend function is going to move your robot just by 100 milliseconds. So maybe let us assume that by calling this friend once, your robot is going to travel 1 centimeter. But if you want to travel 10 centimeters, you need to call this friend 10 times, so that the sensors are going to take care that the front condition is uh, becoming true 10 times, and because of which the front function will be called 10 times. But we don't want this path to be uh, recorded 10 times. So we'll find a way of violating this one after a couple of minutes when I finish writing all the conditions for this one. So as of now, we are up with this forward condition. Now, let me also show you alternative conditions. As I said that the only condition that we need is sensor number 16 and or sensor number 17 needs to be on a black surface so that our robot will move forward. So I can either use digital read 17 to be true or digital read 16 to be true, so that I can put an or condition here by using the pipe symbol available on your keyboard, or you can simply use the condition for just 17 and eliminate the condition for 16, because it is impossible that line number, sensor number 16 is on black surface and 17 is not on the black surface. Because we have a vertical line, it's impossible that your robot is crossing or trying to traverse a particular path in a perpendicular fashion. We are going to either hit with a T, right T, left T, cross condition, or either a straight line. So I'm pretty much sure that whenever I'm writing a condition, either just for 16 and 17, it is going to work in the same manner. So I don't want to write a very lengthy if condition, which is dependent on multiple sensor readings. So that's the reason why I'll be eliminating a couple of conditions. So I'll be simply trying to write the conditions for forward, reverse, right, and left, as well as the conditions, unless they are very strictly required, just only on the basis of sensor number 15, 16, 17, and 18. So let me eliminate these things. So 14 is redundant here. It's optional. If you are interested, you can write it. Otherwise, you can eliminate that. So I want sensor number 15 to be off on white surface. Sensor number 17 to be on black surface. So it's high or true without a negative condition. I want sensor number 18 to be on a white surface. So it will be off. I'm least bothered about sensor number 19. So it's like a don't care condition. I'll delete this. So a condition to assess the front condition, which was earlier dependent on 6 various conditions of the sensors, has been now optimized to just 3 sensors. So what we need is one X sensor, one Y sensor, and one X sensor. That is enough. So similarly, I'm going to write all the conditions for rest of the things by pausing this video for a while and then come back. Okay, so what I have done is I have pasted all the remaining conditions. Now it's time to go through each one of those in detail. As we have already seen the forward condition, now the condition that I have taken for reverse is going to be exactly the opposite of what we have taken for the forward condition. So let me quickly show you what we are about to build. That is, I have taken a small piece of cardboard which is a little bit flexible, and then I have used this polythene plastic tape for building the track, which we'll be using for testing of our maze. Now, as you can see, I have taken this particular shape for taking a U-turn, because it will be easy for us to identify that we need to take uh, a decision of going in a reverse direction whenever we get exactly the reverse of this. So here what's happening is, here we have our sensor 16 and 17 lying on the black line, whereas 14, 15 and 18, 19 lie on the white surface besides like this. So that whenever our three sensor sets are moving ahead, at some point of time, it will either identify that 14, 15 and 18, 19 are on the black surface, whereas 16 and 17 lie on the white surface. So this is one possibility. Other possibility is like you can even take a black tape like this, so that whenever it comes across all the black surface coming in perpendicular with this one, it can either detect this as a cross. So let me show you quickly. If I have a line like this, so if you get a cross like this, then your robot may stop. So I'm simply trying to take a unique condition for every kind of a junction that it is about to identify. So for simplicity and for simplicity of coding, I have simply considered a perpendicular black line to take a U-turn. But here the robot is going to be confused, like when to take a U-turn and when to take a left turn. So here, as you can see, we need to take a left turn as per our standard left wall following algorithm, whereas we have to take uh, a left direction here as well. So how will it identify whether this is a stop condition or a left going condition? So the simple way to overcome this is we have to simply stop here for a certain amount of time, and then move a little bit, maybe like say 1 or 2 inches ahead, and check whether we are again having a line or not. So the simple condition that we can write is, whenever you are getting a back line, it means all the sensors right starting from 14 through 19 are going to become on, and then at that moment we need to push our robot a little bit ahead and check whether we are having a single line or we are still having a black line, and then move backwards and then take whatever decision we need. So let me show you what condition we can write. That is, as of now, I have taken a unique condition where I'll be using the center white and besides left condition. So as you were able to see that for a reverse condition, I have written not 15, not 17, and not 18. It's a meaning that I'm using a perpendicular black line for taking a U-turn. So here I need to simply check for a condition, like whenever I have all the sensors on a black line, I need to simply put another condition. That is, let me copy this. So whenever this happens, I need to simply move 1 inch ahead, and then again check for something. What is that? That is going to be left that is going to be simply left black, center white, and right black. So for this, we need to simply take left black means true, center white means negative, right black means again true. Because wherever we have a black surface, we get a true value. So 1" moving ahead can be copied from our previous code, that is, uh, we can simply type this in. Okay, so let me make some minor modifications. I guess I have used this as motor 1 and 2. So I'll call it motor 1 and this will be motor 4. Okay, so I'm going to move my motor forward by some amount. So I have had some sort of calibration so that whenever I'm moving my robot for 1" uh, I mean for 1 second, then it almost approximately moves by 1" ahead. So I just want to make sure that whenever my robot is hitting a complete black line perpendicular to the path it is following, then I'm going to move 1" ahead and then check whether I attain this condition or not. If yes, then I need to move backwards. I mean completely take a 360-degree turn here. Otherwise, if it's not the condition, then probably I'm going to, so this is my if, else. So I haven't decided yet. Okay, so we'll decide what to do with this. Do something here. Now, similarly, I have written a condition for left. That is, I'm going to simply check whether my all left sensor, that is 14, 15, 16, 17, I mean including the Y sensors and left sensors are high or not. The same is the condition for right. Similarly, we have all the right sensors, like that is 18 and 19 to be high, along with the center sensor 16 and 17. So we are not at all having any not conditions. So whenever you are moving right side, we are least bothered about the left two sensors, that is 14 and 15. And whenever we are moving towards the left direction, we're least bothered about the right sensors, that is 18 and 19. So to some extent, these become the don't care conditions. And now, similarly, we got a cross condition here. That is, all the sensors are going to be on a single line where every sensor is going to give you a positive condition. So you need to take care of certain conditions like this cross condition and our reverse conditions. Both share some common properties. It's meaning that whenever this condition becomes true, at the same moment of time, even your cross conditions becomes true. So how these two differ with each other? So first of all, whenever these three sensors, that is 15, 17, and 18 become true, we have an internal condition of checking whether this is true or not after following a certain amount of direction. So what is going to happen here is, if this condition is attained, then motor will first of all move 1" ahead. Then it will check for this condition. For instance, if this internal condition is false, means if it's not a U-turn, then it will remain there. All these left and right conditions will be false. Then this condition becomes true. And then it's going to move left. So it's not a big deal. Like now we are very much clear with the stuff like what happens if this condition is attained. Our robot moves 1" ahead and it checks for this condition. So if it's not true, then under else condition, I mean if it's not a turn 360-degree back condition, then we need to simply move backwards by the same amount of what it took to move forward. So move an inch ahead, check if it's moving, 360-degree turn. If not, move back and let the remaining conditions get assessed. So it's a simple conditional statement. Simply we are using if and else kind of a condition. And your final program may be varied depending upon your own application and the structure of the sensors which you have. So I have simply tried to cover uh, the kind of conditional statements that we need to put for solving the maze. So basically what we have now is we have initialized the motors. We got a serial monitor for debugging purposes. We have defined the sensors as sensor pins as an input. We have set the speed for a motor, and then we try to release it under setup. And then under loop, the first thing that we are trying to do is we are simply trying to find the junctions. And at the same time, we are also trying to record the path. That is by writing this path equals to plus equals to b, or any sort of character which represents the specific direction. So I'll leave this up to you as an assignment. Like you need to think a little bit like how to avoid the statement of repetitive updation of this particular string character. So as a hint, what I can give you is use some flag statement or use some flag variable, like whenever you make or update this path with b, uh, just make certain flag, like uh, say pf, which stands for path flag equals to 1. It's a meaning that whenever this path flag is equals to 1, I have updated this path, and whenever I try to again update this particular what we call the string variable with b once again recursively, then it should block it somehow. So the only reason is whenever you get a change, like for example, you're following a straight line for about 10 minutes, you need not to every time go ahead and write S condition inside this. So a better way is to use a flag, like making it 1 or 0 to indicate whether you have recently done certain changes in this or not. So another change or another hint that I would like to provide you is try to update this flag under these conditions where we have defined these things like going back or going forward or going right, so that whenever this function is called, you need to first of all identify like a certain function. For instance, I'm calling this back function here. So if I am interested in passing a parameter like back1, it's a meaning that I'm calling it for the first time. If uh, so do I have this function? Okay, so this back will be accepted somewhere here like int I, and then this I will be counted inside this particular back loop. Like I'll be putting a simple if condition, and I'll check if I is less than or equals to 1 or not. So as long as I is equals to 1, I'm ready to update it with another value. As long as it is more than 1, I'm not interested in updating that. So this is a kind of a hint which you need to modify, update in your own program depending upon the type of the sensor structure that you have and depending upon the desired application which you're expecting. So what's next? We need to record the path. We have already done that. So after that, checking if destination is reached by the robot. Okay. So we also have the condition of whether we have reached the destination or not. And if we have reached the destination, then we need to optimize the path. Now, optimizing the path code we have already written inside this. Before that, let me copy paste all the remaining stuff, like the loop ends here. Okay, so I'll copy down the front, back, right, left, and halt conditions first of all into my code, and then the shortened path. So this particular path, the shortened path code is nothing but the optimization code where we're replacing the specific XBX pattern with the respective literal so that the path gets optimized. Let me copy this and paste it after my loop in this program. So our loop starts somewhere here. Just search for the highlighted bracket. Okay, enter and paste it after the loop. Control S for save and Control R for compile. And let's just get this verified whether it's getting compiled or not. I guess there will be an error. Yes. So I think a motor 4, I might have used something else. Yes. So I'll update all these things like M3 replaced with motor 1 and M4 replaced with motor 4. And also we'll be getting another condition. Okay, so we have already defined the string path somewhere at the beginning of our program, so we need not to define it again. So now what happens is the path variable is by default updated whenever we are calling the halt condition at the end of the program. uh, then halt condition itself is going to call the short path function, which is responsible for optimizing the path. So we have already seen how the optimization happens, so I'm not going to get into the details here. So whenever the path is updated, the path is, I mean, the contents of the path is replaced with each of these literals to finally get our result of RL here. And writing the code. So finally, we have covered all these things, these 5 things. That is scanning for the junctions, storing the path, and optimizing, and then finally using this stored optimized path. Okay, so let me quickly introduce you how to uh, use this optimized path. So we have already received the halt condition. Whenever the halt condition is achieved at the end of the program, then it will automatically call the short path. Then this is the path which you already seen in our previous tutorial as per our desired path which we have built for solving the maze. And this path will be down converted into RL as per our standard optimizing algorithm. Now, where is this RL stored? RL is simply stored inside the same path variable, as you can see. Path dot replace this LBL with S, path dot replace LBS with R, and so on. So we are simply trying to override the original string path string variable that was defined at the beginning of this program. And then finally, we are modifying the same path. I mean, initially, whenever the robot was traversing and before it just reaches the halt condition, this is the path which the path variable holds. And by the time this short path function is called and it ends up with the execution of all the statements, then what it will be having is only this path. So you may need to call this short path a couple of times so that you get this. So the better perspective is to call the short path n number of times. So the better way is to count the number of variables, I mean when number of character variables that we have in our string container called path, and then call it those many number of times. So an alternative is we can even check for a function called path.indexOf. So I guess I have already explained this at the time of optimizing uh, video. This is one specific function which replaces a given pattern with the one which we have mentioned on the right side of this, I mean in the form of a second parameter. Another important function that we can use is path.indexOf. So I will be rigorously checking under my path variable for identifying the index of B, which takes care that if I have a B anywhere in this available recorded path, then I'll be getting a return value of some integer, which is definitely a non-zero value. So the least possible pattern that I have is a 3-letter pattern. So if, for instance, imagine that this particular complete pattern will be replaced into just LBL. For instance, let us say this complete string is replaced by this one, then if I implement path dot index of this particular string, then the value which I'll be getting is 1. So from where we are getting that 1 is nothing but the index value of this b. Whereas the index value starts counting from 0, L holds the 0 index, B holds the 1 index. So as long as the path dot index of this string is giving me a value which is a non-zero value, it's a meaning that I still have B remaining in my pattern. So a simple condition is you can somewhere under this loop mention this. So we got this loop here, scan for all the conditions, also scan for the halt condition similar to this one, and whenever we get a halt, call that halt, which will be redirected to this particular line number, and under halt you just check whether the recorded string path dot index of is having a value less than or equals to 1 or not. So as long as the path dot index of this string literal or string variable is giving you a non-zero value, do call this short path function recursively. So that's a simple condition. So this is going to take care that each and every XBX instance in your pattern will be replaced, and ultimately what you'll be getting is RL. Now having said that, we have already shortened the path. Now what we have is RL remaining in the path. Now since this string.path is a global variable, this is now optimized simply RL. Now imagine that your robot has traversed the complete path, and then uh, it has reached the destination. It has recorded the path, it has optimized it, you have connected some buzzer or indicator, or you have given some moment-based indication to the user that whenever your robot has reached the destination, wait for 10 seconds just to be on the safer side, and then put your robot back into the start position. Now, whenever you put this into the start position, you need to write a simple program like read what you have in the path, which is very simple, and scan for the junctions. So next time, whenever your robot is about to iterate the path or cross over through the maze, the first junction whenever it attains, so it could be any kind of a junction. So let us say that it has come across the left moving condition, or it is a left T junction. Then this condition will be triggered again. This time we're not interested in updating the path, but this time we are interested in calling the recorded path value and then move according to that one. So under this, let me comment down this one and show you how to write a code for the second iteration. Now, what we have here is the condition for left T, or simply the left condition. So this is the first junction that your robot is going to encounter with. So if it hits this condition, then we need to check like if simply path dot index of, okay, or we can simply check the condition like, since path being a string which is nothing but a character array, first check path of 0, uh, is R. If it is R, then move right. Where did I write it? Okay. If it is a R variable, then simply move right. I'm simply trying to write it in the form of a statements one below the other so that you can understand this and compare it in a linear fashion. Similarly, if it is an L, move towards left, and if it's a straight, then move front. You will never ever have the B condition because we are already replacing XBX pattern by some other literal. So XBX is definitely replaced with either S or R or L. That's it. But we never ever have any other condition. So as you can see, these are the only possible conditions. That's why we need to simply check for this. So now you can go ahead and uncomment these lines. Now, imagine that you are running your robot for the first time. For the first time, if this hits, this will not be true, this will not be true, this will not be true. Whereas only this will be true, and that's why the things will be appended. The next iteration, I mean for the second iteration, whenever you're trying to uh, execute the robot for the first time, then either of these three conditions will remain true. So again, there is a possibility of using a flag here to indicate whether this is the first iteration or the second iteration, so that whenever the if condition of flag is equals to 1, it's a meaning that you are about to follow the section that is written under a specific snippet of code, I mean, or a specific section of the code. And whenever the flag is equals to 2, it's a meaning that you are running the second iteration and you need not to bother about the updation of your path variable. So these are some of the small hints that you need to keep in mind whenever you're designing your maze following robot. And now finally, uh, you can update all these things and uh, merge up with this particular program to get the things rolling. So in the next video, I'll show you a small demonstration of how the robot solves the maze by itself. That's all for this video course. Thank you. Hello and welcome to the debugging video. Now, as you can see, I have this USB cable already connected to my laptop. And now, as I had shown you in the earlier video, just take a piece of cardboard and use a tape to build some sort of shapes. So what I would recommend you people is build all sorts of junctions whichever are possible, all those 8 junctions which we have seen in our video, so that you can build any sort of junction as and when you are testing your robot. So a couple of things to be kept in your mind whenever you are dealing for the first time, that is whether you have this button or not, whether you have this sort of chassis available, or what kind of motors, what kind of wheels you have. Keep in mind a couple of things. So the first thing is you need to place this chassis in a very structured manner. So I have used these screws and nut bolts to properly maintain a spacing in between. So for the kind of a chassis, if you're getting, if the circumference, I mean, if the overall diameter of this particular chassis is a little bit bigger one, then you can place the battery and the controller on the same plate itself. So I wanted to keep this very small so that I'm just having a diameter of about 6 inches. So it's very tiny, and as you can see, I have the sensor pattern in this way. so that whenever I'm using some sort of sensors, I'm 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 simply trying to program this all the time. I mean, it takes more than 6 to 7 hours to completely build a robot like this if you're sitting continuously uh, with coding being done simultaneously. So what I'll do is I'm simply putting this pattern onto the sensor, and I'm assessing whether it is rotating in a proper direction or not. And not only that, but whenever you feel that your motors that you have received is uh, perfectly matched, even then you will always find some sort of difference in the RPMs of these motors. So a simple solution for this one is to set the so the simple solution here is to set so the simple solution here is to set uh, the speed of the motor. So as you can see here we have uh, let me show you. Okay, so here we have set the speed of our motor to 200. So if you look in my earlier code, you will find that I have written 180 here and I have written 210 here. So depending upon what exactly you're doing, it depends. Like, uh, for instance, if I'm connecting this motor and if I try to roll it, as you can see, it's moving pretty in a straight direction. So you need to go for a couple of iterations first of all, and then you will find like which motor is rotating with a greater speed and which is rotating with a smaller speed. And depending upon a couple of iterations, you need to finally take a decision like whether to increase or decrease the speed. But I would recommend you people to keep the speed a little bit less during the testing phase. So second thing, very important thing is that you can either connect a switch uh, which breaks the positive supply of this battery, or you can simply use two jumper cables and attach them together. And this caster wheel and these two wheels of the motor needs to be on a proper surface, and you may or may not uh, prefer having this one. I mean a sensor similar to this one. So let me show you. So you can prefer having sensors like this or like this. So the only disadvantage that I told you about this one is you need to apply separate VCC and ground to each of this particular IC. Whereas if you're using a common combo IR line sensor array, then the things become pretty much simple. But the advantage that you gain by using this discrete IR sensors is that depending upon the width of your track, you can adjust these things whether to be very much near or very much far away. So here, sometimes you may find like we haven't programmed these last two IR sensors, most of the, I mean for identification of most of the junctions. So if you would have had a sensor like this in bulk quantity, then probably you can even place the sensors one on the top side, one on the rear side, and you can even place these sensors somewhere like this. So I would have preferred mounting the sensors like this. I mean, I would have placed it in a T pattern so that 1, 2, and 3, and the fourth one. So this would definitely make the things easy. Like the pattern which I generally prefer is this. So I would have preferred having the sensors in this pattern. So it's a cross pattern. Wherever, whenever at any given moment of time, if you're scanning this sensor pattern, you will very easily be able to identify, like if I'm getting the left sensor, center sensor, and the bottom sensor on, it's a meaning that I have a left section. If I have the bottom, center, and right sensors on, it's a meaning that I have a right sensor. If I have all the sensor on, it's a meaning that I have a cross condition. So this is the best possible condition, but generally the problem is that we won't find sensors of this kind. So depending upon whether you have the discrete sensors, whether you prefer to have these discrete sensors, or you are going to prefer this line sensor array, you need to program your maze solving robot pretty wisely uh, to cope up with the hardware and the software conditions. And the rest of the conditions remain same as we have discussed in the initial video. So the controller, I mean the Arduino and the motor shield needs to be placed properly. I have used some sort of spacers. In your case, I guess if you have a better spacing available on your bottom plate, then you can probably mount this battery on the bottom plate here itself. So it would even have a better balance as well. So it depends, like depending upon what kind of chassis you'll be getting for this course and what sort of battery you'll be using. You can always go ahead and mount them in the way you need, and then you can probably test it. So this is the custom built robot, especially designed for this course. And now let me show you like how I have been testing this one. So whenever you turn on the power supply, one of the motor rolls initially. So you can consider this as just um, what we call a sort of initialization condition. Go straight and then move left, then find the pattern,